Distributed Systems from Scratch. This is episode 16, CRDTs, Conflict Free Replicated Data Types, the Season 4 opener. Seasons 1 through 3 built a complete foundation: theory, protocols, and real systems. Season 4 goes deeper into the advanced ideas that push the boundaries of what distributed systems can do. We start with CRDTs, arguably the most elegant idea in modern distributed systems: a way to have multiple replicas edit the same data concurrently, offline, without coordination, and have them all converge to the same result automatically. Remember the conflict problem from episode 8? In multi-leader and leaderless replication, concurrent writes can conflict. Two users update the same data at the same time on different replicas. Which write wins? Last write wins, throws away data. Manual merge resolution doesn't scale. Application level conflict handling is complex and error prone. What if the data structure itself could resolve conflicts? What if, by mathematical design, any order of operations always produced the same result? That's exactly what a CRDT is: a conflict free replicated data type. CRDTs are data structures designed so that any order of operations produces the same result. No coordination needed, no consensus protocol, no conflict resolution logic. Replicas merge automatically and always converge. Two replicas can be edited independently, even offline, and when they sync, they merge into the same state. Guaranteed. This sounds like magic. It's not, it's mathematics. The mathematical foundation is a structure called a joint semilattice. Don't let the name scare you. The idea is simple. A CRDT's merge operation has three properties. Commutative: the order of merging doesn't matter. A merge B equals B merge A. Associative: the grouping doesn't matter. A merge B merge C gives the same result no matter how you group it. Idempotent: merging the same state twice doesn't change anything. A merge A equals A. If your merge function has these three properties, replicas will always converge to the same state regardless of the order or number of times they synchronize. This is mathematically proven. CRDTs come in two flavors: state based CRDTs or CVRDTs. Replicas send their full state to each other. The receiver merges the incoming state with its local state using the join operation. This is simple and tolerant of lost or duplicated messages. Since merge is idempotent, receiving the same state twice is harmless. The downside: messages can be large. Operation based CRDTs or CMRDTs. Replicas send individual operations. Increment by 1. Add element X. Operations must be commutative so they can arrive in any order. Messages are small, but the network must deliver them reliably, at least once. In practice, most modern implementations use delta state CRDTs, a hybrid that sends only the state difference since the last sync, not the full state. Best of both worlds. Let's build CRDTs from scratch, starting with the simplest one: the G counter, a grow only counter. Here's how a G counter works. Imagine three nodes: A, B, and C. Each node maintains a vector, one slot per node in the cluster. Node A only increments its own slot. Node B only increments its own slot. Node C only increments its own slot. Node A has incremented three times. Its vector is A colon 3, B colon 0, C colon 0. Node B has incremented five times. A colon 0, B colon 5, C colon 0. Node C has incremented twice. A colon 0, B colon 0, C colon 2. When any two nodes sync, they merge by taking the element-wise maximum of their vectors. Max of 3 and 0 is 3. Max of 0 and 5 is 5. Max of 0 and 2 is 2. The merged vector is A colon 3, B colon 5, C colon 2. The total count is the sum of all slots. 3 plus 5 plus 2 equals 10. No conflicts, no lost increments. The merge is commutative. Order doesn't matter. Associative grouping doesn't matter. Idempotent, merging the same state twice doesn't change the result. This is a CRDT. The G counter can only go up. What about decrementing? The PN counter, positive negative counter, solves this with two G counters. One tracks increments, the other tracks decrements. The P counter says A has incremented 5 times, B 3 times, C once. Total positive 9. The N counter says A has decremented 1 time, B 0, C once. Total negative 2. The current value is P minus N. 9 minus 2 equals 7. Both the P and N counters merge independently using element-wise max. The value is always derived as the difference. Simple, elegant, and conflict-free. Counters are easy, sets are harder. The G set, grow only set, is the simplest set, CRDT. You can only add elements, never remove. Merge is set union. Replica A has apple and banana. Replica B has banana and cherry. Merge apple, banana, cherry. No conflicts possible. Union is commutative, associative, and idempotent. But you can't remove items from a G set. That's limiting. The OR set, observed remove set, solves this. Each add operation generates a unique tag. When you remove an element, you remove specific tags, not the element itself. If another replica concurrently adds the same element with a different tag, both tags exist independently. The remove only affects the tag it knows about. The result, add wins over a concurrent remove. If two replicas concurrently add and remove the same item, the item stays. This is the add wins semantics. For single values like a user's profile name, the LWW register is the simplest option. Each write carries a timestamp. On merge, the write with the highest timestamp wins. Node A writes hello at timestamp 10. Node B writes world at timestamp 12. Merge world wins. It's a valid CRDT. Merge is commutative and idempotent, but it silently drops the losing write. Hello is gone. If both writes carry meaningful intent, data loss is unacceptable. Cassandra uses LWW registers as its default conflict resolution. It works, but it's the bluntest instrument in the CRDT toolbox. The hardest CRDTs are sequence types for collaborative text editing. Each character in a document gets a unique ID, a combination of the node ID and a local counter. When you insert a character, you specify insert after this ID. When two users concurrently insert at the same position, their characters both appear, ordered deterministically by their unique IDs. This is how Google Docs, Figma, and many modern collaborative editors work. The specific algorithms RGA, LSEQ, YJS differ in how they assign positions and handle performance, but the principle is the same. Every insertion is uniquely identified, and concurrent insertions are ordered deterministically. YJS is currently the most popular CRDT library for web-based collaborative editing. It powers extensions for Prose, Mirror, CodeMirror, and many other editors. Let me show you a concrete example. The Dynamo style shopping cart, implemented as an OR set CRDT. A user has two devices. On their phone, while offline, they add headphones and a phone case to the cart. On their laptop, also offline, they add a keyboard and remove the headphones. Both devices come online and sync. The OR set merge. Headphones were added on the phone with tag 1. The laptop removed headphones by removing tag 1, but the phone's ad created tag 1 independently. In the OR set model, the phone's intent to add headphones is a concurrent event with the laptop's removal. Result after merge. The cart contains headphones, phone case, and keyboard. Add wins over a concurrent remove. No data was lost. No manual conflict resolution. The user sees all items they intended to add. This is the same use case Amazon's Dynamo paper described in 2007. CRDTs are the clean solution to the problem Amazon solved with ad hoc vector clock merging. Let me give you the full catalog. Counters: G counter for increment only. Page views, likes, PN counter for increment and decrement. Inventory counts, vote totals. Sets: G set for add only, tags, follower list, or set for add and remove. Shopping carts, collaborative list, registers. LWW register, simple but drops data. MV register, keeps all concurrent values, lets the application choose. Use when data loss from LWW is unacceptable. Sequences are GA and YJS for ordered list of elements. Collaborative text editing, shared document editing. Maps, CRDT maps, where each value is itself a CRDT, enables JSO and like document structures where each field converges independently. State-based sends the full state each sync. Tolerates unreliable networks. Lost messages are fine since merge is idempotent, but bandwidth is high for large states. Operation-based sends just the operation, very bandwidth efficient, but requires reliable delivery. If an operation is lost, replicas diverge. Delta state CRDTs are the modern sweet spot. They track what's changed since the last sync and send only the delta. Small messages like operation based, tolerant like state based. Most modern CRDT libraries use this approach. CRDTs aren't a silver bullet. Four real limitations. Metadata overhead. A G counter needs one slot per node in the cluster. An OR set stores a unique tag for every add operation. As the system grows and operations accumulate, metadata can become significant. Limited operations. Not every computation can be expressed as a CRDT. Anything that requires a global constraint, like account balance, must be non negative, can't be enforced locally. You need coordination for that. Semantics can surprise, or sets add wins over remove seems reasonable, but it might not match user intent in every case. Choosing the right CRDT semantics for your use case requires careful thought. Garbage collection. Deleted elements leave tombstones. These accumulate over time. Cleaning them up requires all replicas to agree that a tombstone is no longer needed, which ironically requires coordination. The coordination free data type needs coordination for cleanup. CRDTs are in production at serious scale. React, one of the first databases with native CRDT support. Counters, sets, maps, and flags, all as first class data types. Automatically merged during read repair. Redis Enterprise uses CRDTs for active-active geo-replication. Two Redis clusters in different regions, both accepting writes, merging via CRDTs. Automerge, a JSON CRDT library that supports rich text, objects, and arrays. The flagship library for local first application development. YJS, the high performance CRDT library for real time collaborative editing, powers many web based editors. Figma, their collaborative design tool, uses a custom CRDT, allowing hundreds of users to edit the same design simultaneously with zero conflicts. CRDTs enable a new paradigm: local first software. The idea: your data lives on your device first, not on a server. Every edit happens locally with zero latency, no server round trip. The application works fully offline. When connectivity returns, devices sync using CRDTs, conflicts are resolved automatically. The server, if there is one, is just another peer. It helps with sync and backup, but it's not required for the application to function. This inverts the cloud model. Instead of your data lives on our servers and we let you access it, local first says your data lives on your device and you can choose to sync it. Instant edits, offline capable, user owned data, privacy by architecture. This is what CRDTs make possible. Let me connect CRDTs to everything we've covered. Strong eventual consistency from episode 5. CRDTs provide exactly this guarantee. Any two replicas that have received the same set of updates are in the same state. The multi-leader conflict problem from episode 8. CRDTs are the mathematical solution. No more last right wins data loss. Vector clocks from episode 3. Many CRDTs use vector clocks internally for causal tracking. The G counter is a vector clock. Gossip from episode 12. State based CRDTs propagate naturally via gossip. Send your state periodically. Merge on receive. And the CAP theorem from episode 4. CRDTs achieve the strongest possible form of AP, fully available, fully convergent, zero coordination. Let's recap. 1. CRDTs are data structures where any merge order produces the same result. This is mathematically guaranteed by the semi-lattice properties: commutative, associative, idempotent. 2. G counter uses a vector with one slot per node. Merge is element-wise max. PN counter adds subtraction via two G counters. 3. OR set supports add and remove with add wins semantics, used for shopping carts and collaborative features. 4. Limitations are real: metadata overhead, limited operations, surprising semantics, and tombstone accumulation. 5. Local first software uses CRDTs for offline capable, collaboration ready applications. This is the future of personal computing. Next episode: Geo distributed systems, Google Spanner, TrueTime, and CockroachDB. How do you maintain strong consistency when your replicas span continents and the speed of light itself is the bottleneck? We'll see how atomic clocks, GPS receivers, and Paxos combine to make the impossible merely very expensive. That's episode 16. CRDTs, data structures that resolve conflicts through mathematics, not coordination. Next time, geo distributed systems. Thanks for watching.